Hello, I'm Sri from CBTU. CBTU presents a course on Big Data on Hadoop, Module Hadoop, Section Hadoop Architecture. As we have seen in the previous session, Hadoop has master-slave architecture. A Hadoop HDFS cluster consists of a single name node and there can be a number of data nodes. Name node or master server manages the file system namespace and regulates access to files by clients. Data nodes manage the storage attached to the nodes. HDFS exposes the file system namespace and allows user data to be stored in files. Hadoop 2.0 is a framework for processing, storing, and analyzing massive amounts of distributed, unstructured data. Hadoop Common. This contains libraries and utilities needed by other Hadoop modules. This is a distributed file system that stores data on commodity machines, providing very high aggregate bandwidth across the cluster. Hadoop YARN is a resource management platform responsible for managing computing resources in clusters and using them for scheduling users' applications. Hadoop MapReduce is an implementation of MapReduce programming model for large-scale data processing. Hadoop Common contains libraries and utilities needed by other Hadoop modules. Provides file system and operating system level abstractions, a MapReduce engine, and the HDFS. It also contains the necessary Java archives, jar files, and scripts needed to start Hadoop. HDFS maintains location rack info where the worker node is. Hadoop applications can use this information to execute code on the node where the data is lying. HDFS replicates data for data redundancy across multiple racks. Impact of rack power outage or hardware failure is none, as data remains available always. This is high-level architecture of Hadoop. A Hadoop cluster includes a single master and multiple worker or slave nodes. The master node consists of job tracker, task tracker, name node, and data node. A worker node or slave node can act as both data node and task tracker. In a large cluster, HDFS nodes are managed through a primary name node server to host the file system index and metadata. A secondary name node that can generate snapshots of name nodes' memory structures, acting as a backup. A standalone job tracker server can manage job scheduling across nodes. When Hadoop MapReduce is used with an alternate file system, the name node, secondary node, and data node architecture of the HDFS are replaced by the file system specific equivalents. Daemons are continuous processes that run in the background, like HTTPD, SSHD. Hadoop also have 4 daemons which need to run when big data analytics application is running. Daemons are name node, secondary name node, data node, resource manager. It's easy to check Hadoop daemons are the Java processes running with JPS command. JPS is JVM process status tool. Java Virtual Machine Process Status Tool. JPS comes with Sun Java JDK. The name node and data node are pieces of software designed to run on commodity machines. These machines typically run a GNU Linux operating system. HDFS can be deployed on a wide range of machines. HDFS is built using the Java language. Name node or the data node can run on any machine that supports Java. A dedicated machine may run name node software and other nodes in the cluster may run an instance of the data node software. The name node is the controller and repository for all HDFS metadata. This system is designed in such a way that user data never flows through the name node. Each data node sends a heartbeat message to the name node periodically. The name node marks data nodes without recent heartbeats as dead and doesn't forward any new input-output requests to them. Name node constantly tracks which blocks need to be replicated. In order to avoid replication issues, this timeout value can be reduced. The timeout can be shorter interval to mark data nodes as stale and avoid stale nodes on reading and writing by configuration for performance sensitive workloads. The timeout to mark data nodes dead is around 10 minutes by default, and this is configurable. HDFS implements data integrity for files by implementing checksum checking and eliminates corrupt block of data. When a client creates a HDFS file, it computes a checksum of each block of the file and stores this checksum in a separate hidden file in the same HDFS namespace. When a client retrieves the file contents, it verifies that the data it received from each data node matches the checksum stored in the associated checksum file. If not, then the client can opt to retrieve that block from another data node that has a replica of that block. The FS image, file system image, and the edit log are the central data structures of HDFS. Name node is configured to support maintaining multiple copies of the FS image and the edit log. Any update to either FS image or edit log causes each of the FS images and edit logs to get updated synchronously. When a name node restarts, it selects the latest consistent FS image and edit log to use. Snapshots support storing a copy of data at a particular instant of time. Snapshots are useful to roll back a corrupted HDFS instance to a previously known good point in time. Default replication factor is 3 data nodes for writing data. Name node maintains a list of data nodes where blocks reside. The client writes to the first data node, which will replicate to the other data nodes in the list. The data is pipelined from one data node to the next. HDFS can be accessed from applications in many different ways. Natively, HDFS provides File System Java API for applications to use, a C language wrapper for this Java API, and REST API is also available. In addition, HTTP browser can also be used to browse the files of a HDFS instance. HDFS can be mounted as part of the client's local file system. HDFS allows user data to be organized in the form of files and directories. It provides a CLI called FSShell, file system shell, that lets users to interact with the data in HDFS. We're going to cover these access methods in the coming sessions. Thanks for watching.